Today, I'm covering a mix of topics including corporate strategy, public policy, and breakthrough technology shaping the hydrogen industry. I'll start with ExxonMobil's CEO Darren Woods, who recently discussed how hydrogen fits into the company's long-term energy strategy. As one of the largest oil and gas companies in the world, ExxonMobil's pivot toward hydrogen represents a significant shift in the energy landscape. The company is focusing on blue hydrogen produced using natural gas with carbon capture and storage, and sees this as a major pillar of its low-carbon transition. I'll break down how ExxonMobil's approach compares to other energy giants like BP, Shell, and TotalEnergies, all of which are making major investments in both blue and green hydrogen. I'll also examine the economic impact of these investments, considering factors such as production costs, government incentives, and long-term profitability. Next, I'm going to turn to a new initiative in Seattle where Modern Hydrogen has partnered with a regional utility to develop methane pyrolysis technology. Unlike traditional blue hydrogen production, which relies on CCS, methane pyrolysis separates hydrogen from natural gas while generating solid carbon as a byproduct instead of CO2. This method presents a potential breakthrough for cost-effective hydrogen production, and I'll discuss the economic feasibility of scaling this technology and how it fits into the broader energy transition. From there, I'll shift to Pennsylvania, where Governor Josh Shapiro recently announced a plan to fast-track hydrogen power plant projects with new subsidies and regulatory support. Pennsylvania's strategic location and abundant natural gas resources make it an ideal hub for blue hydrogen production, but the question remains whether these incentives will be enough to attract long-term investment. I'll analyze the projected economic impact of Pennsylvania's plan, including job creation, infrastructure investment, and potential hydrogen exports to neighboring states. Finally, I'm going to explore the aviation industry's latest breakthrough in hydrogen technology, a new hydrogen-storing jet fuel that has the potential to revolutionize air travel. This innovative fuel uses liquid organic hydrogen carriers, or LOHCs, that allows hydrogen to be stored at room temperature, solving one of the biggest challenges of hydrogen-powered aviation. I'll discuss the economic and logistical benefits of this technology, the companies investing in hydrogen-powered aircraft, and the timeline for commercial adoption. All of this on today's Hydrogen Podcast.
So the big questions in the energy industry today are: how is hydrogen the primary driving force behind the evolution of energy? Where is capital being deployed for hydrogen projects globally? And where are the best investment opportunities for early adopters who recognize the importance of hydrogen? I will address the critical issues and give you the information you need to deploy capital. Those are the questions that will unlock the potential of hydrogen, and this podcast will give you the answers. My name is Paul Rodden, and welcome to the Hydrogen Podcast.
ExxonMobil's CEO, Darren Woods, has reaffirmed the company's commitment to hydrogen, positioning it as a key pillar of its low-carbon energy strategy. The company is focusing primarily on blue hydrogen, produced from natural gas with carbon capture and storage. This aligns with ExxonMobil's broader efforts to leverage its existing natural gas infrastructure while reducing emissions. The company is currently developing one of the largest blue hydrogen production facilities at its Baytown refinery in Texas. Expected to come online by 2028, the facility will produce approximately 1 billion cubic feet of hydrogen per day, with captured CO2 stored underground to minimize emissions. Financially, ExxonMobil has allocated $17 billion for low-carbon investments through 2027, with a significant portion dedicated to hydrogen and CCS projects. However, ExxonMobil's approach is facing competition from other energy giants that are investing in both blue and green hydrogen. Companies like BP, Shell, and TotalEnergies are diversifying their hydrogen portfolios by developing large-scale electrolyzer powered by renewable energy, which could ultimately be more cost-competitive as technology advances. The economic viability of blue hydrogen heavily depends on government incentives, such as the U.S. Inflation Reduction Act, which offers up to $3 per kilogram of hydrogen in production tax credits. Without these incentives, the cost of blue hydrogen, currently estimated between $1.50 and $2.50 per kilogram, could rise, making green hydrogen a more attractive alternative in the long run. Additionally, the growing interest in natural hydrogen, which is naturally occurring in the Earth's crust, could disrupt the market by providing low-cost, zero-emission alternative. ExxonMobil's long-term strategy will need to adapt to these evolving economic and technological factors. Next, Seattle-based Modern Hydrogen is pioneering a new method of hydrogen production using methane pyrolysis, which extracts hydrogen from natural gas while producing solid carbon instead of CO2 emissions. This method offers a lower carbon alternative to traditional blue hydrogen and eliminates the need for expensive carbon capture and storage infrastructure. The company has partnered with a major regional utility to test the feasibility of integrating methane pyrolysis into existing gas pipelines, with the goal of gradually transitioning from natural gas to a hydrogen-based energy system. Economically, methane pyrolysis presents a cost advantage over green hydrogen. Green hydrogen produced via electrolysis currently costs between $4 and $6 per kilogram due to high electricity prices and limited renewable energy availability. In contrast, methane pyrolysis has the potential to produce hydrogen for under $2 per kilogram, making it a more financially viable option in the short term. Furthermore, solid carbon byproduct can be used in various industrial applications such as battery production, concrete manufacturing, and agriculture, creating additional revenue streams for companies adopting this technology. Scaling methane pyrolysis remains a challenge, as current production volumes are relatively small. However, if successful, this method could play a crucial role in decarbonizing natural gas infrastructure while offering an affordable pathway to clean hydrogen. Policymakers and investors are closely watching modern hydrogen's progress, as its success could influence future hydrogen funding and regulatory decisions. Next, Governor Josh Shapiro's newly announced hydrogen initiative aims to fast-track the development of hydrogen power plants and industrial hydrogen projects in Pennsylvania. The state has already been selected as one of the 7 regional hydrogen hubs receiving federal funding, and this new plan seeks to accelerate investment by offering a combination of tax credits, grants, and regulatory streamlining. Pennsylvania's strategic advantages include its abundant natural gas reserves, existing pipeline infrastructure, and proximity to major industrial centers. The plan is projected to generate $3 billion in new investments over the next 5 years and create up to 20,000 jobs in construction, engineering, and manufacturing. Additionally, Pennsylvania is positioning itself as a regional hydrogen supplier with potential export opportunities to neighboring states. While the plan has strong economic potential, its success will depend on the cost of hydrogen production and the willingness of industries to transition from natural gas to hydrogen. If hydrogen remains expensive, power plants and industrial users may hesitate to make the switch without additional incentives. The state's long-term goal is to establish a competitive hydrogen economy that can attract private investment and reduce reliance on government subsidies. And lastly, in recent developments, the aviation industry is exploring innovative methods to integrate hydrogen as a sustainable fuel source. One of the most promising advancements involves liquid organic hydrogen carriers, or LOHCs, which present a practical solution for hydrogen storage and transportation. Unlike compressed or cryogenic hydrogen, which require high pressure tanks or extreme cooling, LOHCs remain in a liquid state under ambient conditions. This eliminates many logistical and safety challenges while making hydrogen-powered aviation a more viable solution. The way LOHCs work is through a reversible hydrogenation and dehydrogenation process. First, the LOHC absorbs hydrogen in a reaction that occurs at elevated pressures, typically between 30 and 50 bar, and moderate temperatures of around 150 to 200 degrees Celsius. This reaction is exothermic, meaning it releases heat, which must be carefully managed to ensure system efficiency. Once absorbed, the hydrogen-rich LOHC can be transported and stored, much like conventional jet fuel. And when the hydrogen is needed, the LOHC undergoes dehydrogenation, where the hydrogen is released at temperatures between 250 and 320 degrees Celsius. This process is endothermic, requiring an external heat source, but with efficient thermal management and waste heat recovery, the system can be optimized for better overall energy efficiency. From an economic perspective, the adoption of LOHC technology in aviation introduces several important considerations. The infrastructure investment required for hydrogenation and dehydrogenation facilities will be significant, as airports and aviation hubs will need to accommodate this new fuel handling process. Additionally, the integration of LOHC technology into aircraft design itself requires modifications, further increasing upfront capital costs. However, the operational costs of hydrogen-powered flight could become competitive with conventional fuels if the right efficiencies are achieved. By incorporating advanced thermal management and waste heat recovery systems, energy consumption can be minimized, improving overall economics of hydrogen flight. And fuel production costs remain a key factor in determining the feasibility of LOHC-powered aviation. The economic viability of this transition will depend heavily on the cost of LOHC materials, the efficiency of hydrogen production, and the ability to scale these technologies. Recent research on hydrogen-based aviation highlights the need for high-efficiency fuel cell systems and optimized onboard storage solutions. Studies indicate that in order to make hydrogen-powered regional aviation competitive, significant technological advancements are required in both hydrogen storage and propulsion systems. Now, as these technologies mature, LOHCs have the potential to play a transformative role in sustainable aviation. By addressing challenges related to efficiency, material stability, and infrastructure development, hydrogen-based flight could become a major player in decarbonizing the aviation industry. Given the growing number of investments in hydrogen fuel cell technologies, it's only a matter of time before we see real-world implementation of these advancements in commercial air travel. The aviation sector, which has long struggled to find scalable solutions for reducing emissions, may finally have a breakthrough that balances sustainability with economic viability. All right, that's it for me, everyone. If you have a second, I would really appreciate it if you could leave a good review on whatever platform it is that you listen to. Apple Podcasts, Spotify, Google, YouTube, whatever it is. That would be a tremendous help to the show. And as always, if you ever have any feedback, you're welcome to email me directly at info@thehydrogenpodcast.com. So until next time, keep your eyes up and honor one another.
Hey, this is Paul. I hope you liked this podcast. If you did and want to hear more, I'd appreciate it if you would either subscribe to this channel on YouTube or connect with your favorite platform through my website at www.thehydrogenpodcast.com. Thanks for listening. I very much appreciate it. Have a great day.